Okay, this is part 3 of the lecture on relativistic dynamics. The lecture is intended for Honors Physics A, B, and AP Physics C. Okay, here's the situation that I'm going to set up. We're going to take an object here of rest mass m naught, and it's going to begin at rest with respect to an inertial reference frame. And then a net force is going to be applied to the object horizontally like so, and we're going to accelerate the object up to the speed v. Okay, what we're going to do is we're going to apply the work energy theorem to that situation. So let's draw out the situation like so. Okay, so apply the work energy theorem to the following. Okay, so right here is our object of rest mass m naught, and it begins at rest, right? So, like so, with respect to an inertial reference frame. And then we have a net force that's applied like so. We'll just call it F horizontally. The object then ends up over here. It has a relativistic mass m. Notice that the relativistic mass expression is still here on the board, and it has the speed v. Okay, now go all the way back to chapter 7 and recall the work energy theorem. That work is equal to change in kinetic energy. Okay, let's immediately begin by writing the final expression here on the right-hand side of the expression in the following way. Okay, we're going to have a final kinetic energy here. I'm just going to refer to it as K, and then minus the initial kinetic energy over here, which is equal to 0 because the object begins at rest, like so. So suffice it to say, the right-hand side of the expression is just the final kinetic energy. We'll call it K. Okay, and then the left-hand side of the expression. The left-hand side of the expression is our net work calculation, and recall from chapter 7 that that's done in the following manner. Like so. Now, of course, back in chapter 7, when you learned the work energy theorem and specifically how to calculate work, it was done algebraically. It was basically just force times distance. And then we looked at all the situations involving the dot product as we did back in chapter 7 leading into chapter 8. However, in this case, we have to write this as an integral. And the reason for that is because we can no longer write the net force F here as mass times acceleration. The reason why is because the mass is continuously changing as the object accelerates. So then therefore, we have to write the net force F in its most general way, which was originally written by Newton back in Principia in 1687. Recall that the net force from chapter 9 is also the same thing as the change in the momentum of the system with respect to time. Like so. So now let's go ahead and perform this integral. In order to do so, the first step is actually just algebraic. Let's go ahead and switch these two terms here like so. Like this. And then this right here is derivative of position with respect to time, which is velocity. Like so. Okay, now the variable that we're integrating over. The variable that we're integrating over is the momentum p. Now recall that momentum is mass times velocity, where the mass is the relativistic mass. Like so. And then contained within this expression for momentum is v, the variable that appears here in the integrand of our expression. So then therefore, what process do I have to use from calculus in order to integrate this quantity where p right here is in fact a function of v? We have to use integration by parts. Okay, now in terms of these variables, here's then what the integration by parts looks like. So we have here the final kinetic energy K, now equal to this integral. Okay, using integration by parts, that integral is now written like this. Like so. So of course in calculus, you learn integration by parts in terms of the letters u and v. Here in terms of the variables that we have present in this calculation, that's what the integration by parts looks like. Okay, let's go ahead now and start filling in these terms. So first of all, I have p times v. So this multiplied by v so, and then minus the integral, where the integrand is the momentum p. And we're integrating now over the velocity v. technically it's the speed, however, in this easy calculation. So we're going to start off initially at rest, remember, and with a final speed v. Okay, let's take a look at the integral here all by itself. Let me just pull that off to the side, like so. So here's the integral. I'll use a different color. All right, so the variable that we're integrating over here is v, so then therefore performing this integration is actually rather easy to do. We're just going to use a little bit of u substitution. So what I'm going to do is I'm going to set u equal to this quantity here, like so, which is underneath this radical sign. So let's go ahead and differentiate it. It looks like this, like so. And now contained right up here in the integral is a v dv, which is right here. So now let's go ahead and switch variables. Okay, so switching variables, let's now see what I get. So first of all, I've got m naught, which is the constant, and then multiplied by these guys here, moved over to the other side of the expression. And now let me go ahead and plug in my new variable u. So when I switch variables here using u substitution, I end up with this quantity right here. Okay, let me move now to the far right-hand board to finish this integral, and then when I do, we'll eventually plug it in right here in this blue expression. Okay, so first of all, I've got some constants here. Let me go ahead and pull those guys out like so. Okay, let me just rewrite this. Like so, and then of course recall the rule for integrating a polynomial. We'll take here the value of the exponent, increase it by 1, and then divide by that new exponent. So, okay, the 2's cancel out, so let's go ahead and get rid of those guys. Okay, now let me go ahead and switch my variable back to in terms of being in terms of v, that is. Like so. And now we integrate between 0 and v. So plug in the upper limit of integration into the expression first, and you basically just get the expression when you do. So, and then minus with the 0 plugged in. So minus a negative gives you then this. Like so. Okay, so that's the result of the integral. I basically can't go any farther than that with that term. So let's go ahead and plug it in here. When I do, however, let's keep in mind that I'm subtracting. So I am going to have to distribute my negative sign. So let's be a little bit careful of that. Okay, let me do some erasing here. Okay, so now kinetic energy K is equal to, first of all, this term right here. Like so. And then minus my integral, so minus that. Okay, let's distribute the negative sign through carefully. Like so, and that leads me to here. Okay, at this point, let me do some erasing. All right, so I don't need any of this stuff anymore. Let's get rid of all of this. Like so. And now when I get to this step here, you look at this and you're like, okay, well, what does this mean? Let's interpret this expression. In order to interpret this expression, what I'm going to do first, I'm going to add together these two terms. I'm going to do so by getting a common denominator between them. That common denominator is going to be the radical sign. So let's go ahead and rewrite those first two terms in the following way, now with a common denominator. Like so. So take a look at that carefully. Notice how I added these two terms here by getting a common denominator, but then I still have this little guy here. So, okay, let me go ahead and get rid of this now. Okay, let's go ahead and simplify this numerator. So when you simplify the numerator here, notice that you have an m naught v squared and then minus an m naught v squared. The c squareds cancel out. So that term drops completely. And then I'm left with an m naught c squared times 1 in the numerator of the expression. And then take a look at this right here in the first term. Notice that the relativistic mass appears. That then gives us this. So, and now let's interpret this expression. We're going to interpret this expression in the following way. We're going to write this as total energy E. The total energy E of a system, all forms of energy that are present, are all of those forms added together. Now, one of those forms we're familiar with, and that's the energy associated with motion. That's kinetic energy K. In order to get all the terms, however, to be positive in this expression, the total energy is just the sum of the individual terms. Let me go ahead and move this term here to the other side, such that we then end up with this. Like so. And now here's how we interpret this expression. First of all, right here is the energy associated with motion, kinetic energy K. And then we've got this term here that I picked up a while ago in my integration, but I haven't said anything about. What is this expression right here? This expression right here is referred to as the rest energy. It is specifically this expression right here that is the expression that you always see on posters involving Albert Einstein, the famous equation mc squared. Okay, now, this term right here, the rest energy, is basically saying the following. It's saying that 1 kilogram of mass, m naught, is the same thing as m naught c squared amount of energy, where c squared is 3 times 10 to the 8th squared, which is 9 times 10 to the 16th. So in other words, 1 kilogram of mass is the same thing as 9 times 10 to the 16th joules of energy. This is, in part, the portion of the famous equation E equals mc squared. So you always see this expression written on posters, and it's specifically actually referring to this term right here. If the object is moving, however, at the same time, in addition to its rest energy, we also have the kinetic energy K. So then therefore the total energy E is this quantity of mc squared. Therefore, E equals mc squared. Congratulations, you have seen the derivation of E equals mc squared. Less than 1% of the human population ever sees the derivation. This is the derivation itself. Okay, now, problem-wise, how are we going to approach E equals mc squared involving basic problems? Well, the first thing that I'm going to do is I'm going to go back to the collision situation from parts 1 and 2 of this lecture. I'll do that in part 4 of the lecture to be coming up.